morning, everyone. My name is Daixin Wang from Tsinghua University. I feel honored to be here to present our work, Structural Deep Network Embedding. The work is collaborated with Professor Peng Cui and Wenwu Zhu. Nowadays, networkers are ubiquitous in the real world, ranging from the internet, like social networks, to Internet of Things, from engineering, like transportation network, to science, like biology networks. Analyzing networks has been a fundamental to understand and model complex systems in many fields, such as biology, physics, and social science. However, real-world networks are in large scale. For example, Facebook has more than 1 billion users in total, and each user has over 130 friends in average. Therefore, it forms a big network. Then, how to propose a method to deal with a large network is very important. Traditional network analysis methods often represent the network in the form of G equals to VE. Then, for specific network applications, they design specific network analysis methods to solve them. For example, the graph curls is usually used to perform the node classification in networks, and relational learning is usually used to perform link prediction in networks. However, they have the following two bottlenecks. Due to the existing of the linkages between the vertexes, it is difficult for traditional machine learning methods to work, and it is difficult for them to parallel. Therefore, they suffer from the scalability problem. To address this problem, a question was posed that whether we can learn network limitations that can support network applications. To achieve this, we have two objectives. First of all, the learned network reputations should reconstruct the original network, and second, it should support network inference. By achieving this, the network limitations can preserve the structured information within the network and thus support many network inference applications, such as the classification, clustering, link prediction, and so on. Then, by performing the network embedding, we can directly conduct the existing machine learning methods to the learned network limitations to solve specific network applications, and it is easy for them to parallel because we have encoded the edge information into the learned representations. Then, to perform network embedding, it has the following two fundamental problems in accordance with the two objectives. The first is that we should find a projection function to embed the network and reconstruct the network. However, as many literatures have stated that the network structure lies in a highly nonlinear space. Therefore, the mapping function should be highly nonlinear. Second, to perform network inference, the mapping function should preserve the network structure. However, due to the sparsity of the network, if we only utilize the observed links in networks, it can often get not satisfactory performance. Therefore, we should utilize some other structured information beyond the pairwise relationships. Existing network embedding methods can be classified into two categories. The first is Laplacian-based methods, like some earlier work, LLE and ISOMAP. They first construct the Laplacian matrix and only preserve the pairwise relationship. However, as we have said earlier, only utilizing the observed links cannot perform good performance of network inference. Then, the second category is some structure-based methods, like some recent work, deep work, line, and graph. They are all channel models and utilize high-order information to preserve the structured information. However, channel models cannot capture the highly nonlinear network structure. Consider their limitations. We propose a model named Structural Deep Network Embedding. First, to solve the nonlinearity problem, we use a deep neural network-based model which has multiple layers of nonlinear function to learn the embedding functions, which we call deep network embedding. Then second, to preserve the network structure, we use both first-order proximity and second-order proximity to preserve the structure. Now, let's use a picture to illustrate what is first-order proximity and second-order proximity. In the picture, the first-order proximity indicates that the first and third vertex should be similar because they are directly linked by an edge in a network. The second-order proximity indicates that the first vertex and the second vertex, although they are not directly linked by an edge, but they have many common neighbors. Therefore, they should be also similar with each other in the embedding space. Then we combine the first-order proximity and second-order proximity and use it as a constraint when learning the network embedding. However, the idea faces the following two challenges. The first is how to deal with the network data in deep neural networks. Most of existing deep learning models often deal with the data samples which are independent with each other. Few of them deal with the network data, especially learning representation for networks. Then the second challenge is how to preserve the first and second order proximity in deep neural networks. To address these challenges, we propose the following framework of SDNE. We propose an unsupervised deep autoencoder to preserve the second order proximity and borrow the idea of Laplacian agent maps to preserve the first order proximity. In detail, to preserve the second order proximity, we use the vertex neighborhood structure as the input to the autoencoder, and by using several nonlinear functions to embed it into the embedding space. Then we use several nonlinear functions to embed it into a reconstruction space. Then by minimizing the reconstruction error, the representations in the embedding space can preserve much of the useful information of the input. That is the vertex neighborhood structure. Therefore, it can preserve the second order proximity. Now, let's use an example to illustrate it. Suppose that the vertex I and the vertex j have similar neighborhood structure. Then, by embed it into the embedding space, it can have the similar representations in the embedding space. Therefore, it can preserve the second order proximity. Now, let's look at the loss function. It has a balancing weight B. This means that we will focus more on the reconstruction error of the non-zero element than zero element. The reasons for this are twofold. First of all, because the number of the non-zero elements is far less than the number of zero elements, it is biased. And second, the non-zero element in the network necessarily indicates the similarity between two vertices. However, the zero element in the network does not necessarily indicate the dissimilarity between vertices. So when reconstruction, we should put more weight on the reconstruction error of the non-error element. So we use B here. Now, to preserve the first order proximity, we borrow the idea of Laplacian agent maps and propose the following loss functions, which incurs penalty when similar vertices are mapped far away in the embedding space. In this way, if two vertices are directly linked by an edge in the original network, they should have similar embedding in the embedding space. Then, by combining the loss function of the second order proximity and first order proximity into the unified model, our model can map the network into the highly nonlinear space to preserve the structural information within the network. By optimizing the model, we first use layer-wise pre-training to get better parameters and use the backpropagation on the loss functions to get optimal parameters of the model. Now, let's look at if we want to get the embedding of out of samples. It has the following two cases. In the first case, if the relation of the new vertex to existing vertices is known, then we can get the adjacent vector of the new vertex, and we can directly feed the adjacent vector to the learned SDNE to obtain its embedding. The complexity for it is constant. Then, if the relation of the new vertex to existing vertices is unknown, state-of-the-art network embedding methods cannot handle it. We can resort to other side information, such as the attributes of the vertex, which we leave as a future work. The training complexity is linear to the number of vertices, which demonstrates the scalability of this model. Now, to comprehensively evaluate the performance of network embedding methods, we conduct experiments on 5 data sets. 3 of them are social networks, 1 citation network, and 1 language network. Some of these networks are sparse, and some of them are full connected. Some of them are unweighted, and some of them are weighted. Then we perform the network reconstruction to evaluate the performance of achieving the goal of reconstruction. And we conduct experiments on node classification and link prediction to evaluate the performance on the goal of network inference. Then to give further insights of the network embedding methods, we perform the visualization task. For baselines, we use 4 state-of-the-art network embedding methods as baselines and use common label as the baselines for link prediction. Now, let's move to the performance on the 4 tasks. For task 1, network reconstruction, we first use different network embedding methods to learn the network representations and use the nearest neighbor to predict the existing links. We report the precision at k in the following 2 figures. The higher the curve, the better the performance. From the figure, we can see that our method can achieve 16% improvements over baselines in archive and 85% improvements on block catalog. Specifically, our method can almost perfectly reconstruct the network of archive. This all demonstrates that deep learning models can better reconstruct the network. Then, for the task 2 of node classification, similarly, we also use different network embedding methods to learn the network representations and use the representations of the labeled nodes to train a linear classifier and use the classifier to classify the rest test data. The better the classification performance, the better quality the network representations. Now, we report the F1 score in the following 2 figures. The red curve is the performance of our method, and the higher the curve, the better the performance. From the figure, we can see that our method can achieve over 10% improvements over baselines. Specifically, we can see that when the label data is limited, our method can achieve more significant improvements than the case that the label data is abundant. It is a very good characteristic because in the real world, the label data is often limited. In addition, the performance of our method is much more better than the performance of LE, which only utilizes the first-order proximity. It indicates that only utilizing the first-order proximity to preserve the structural information is far less enough. Then, for the task 3 of link prediction, we also use different network embedding methods to learn the network representations and use nearest neighbor to predict the future links. We report the precision at k in the following table, and the larger the values, the better the performance. From the figure, we can see that SDNE can perform better performance than baselines. Specifically, for k is larger than 800, our method can improve at least 15%. And when k is smaller than 1,000, our method, the precision of our method, can keep at least 19%. It is also a good characteristic because in many real-world applications, people are more concerned about the precision of the results ranking ahead, such as recommendations and retrieval system. In addition, we can also see that SDNE is much better than LE. It also demonstrates that only utilizing the first-order proximity is not enough. Then, to give us some further insights of the network embedding methods, we perform the task of visualization. The task is that we use different network embedding methods to learn network representations and use TSNE to lay out the network. For different vertexes of different categories, we put different colors. And we show the visualization result in the following figure. As we can see in the figure, our method can achieve small within-class distance and large between-class distance. It demonstrates that our network embedding methods can capture the discriminative information within the network and can achieve better visualization result. Now, we make a conclusion of this paper. We propose a structural deep network embedding method in this paper, and we evaluate the network representations on 4 network applications: reconstruction, node classification, link prediction, and visualization. The results on 4 tasks demonstrate the superiority of our methods compared with state-of-the-art. Then, after the paper, we also make the following 3 findings. First of all, network embedding is an effective way to perform on many network applications. Second, although deep learning models always deal with the data samples which are independent with each other, it is also promising to deal with the network data. Finally, preserving the structural information within network, the first-order and second-order proximity, especially the second-order proximity, is important for the network inference. That's all. Thank you.
In training your embeddings, how does the method scale? How big networks can you apply it to?
The largest data set of our method is about 100,000 vertexes. Yeah. How long you take? It will take about less than a week. Yeah.
Okay. Hi. Thanks. This is really interesting work. Have you thought about doing a denoising autoencoder?
Yeah.
So is that what that's what these results were, or?
No. I not use the denoise autoencoder. It is a basic autoencoder.
Okay.
Because the vector of the input is very sparse, and if we also use a denoise autoencoder, the information will lose much more.
Okay. Thank you.
Hi. I was wondering how the size of the central, the low-dimensional representation affects the performance of your algorithm.
The experiment, the figures are using the 100 dimensions and report the result, and we also change the dimension from the 50 to 200, and the results is reported in the paper.
Can you summarize them in a few words?
That is when the dimension of the embeddings increases, the performance will increase at first, and when the dimension continually increase, and the performance will decrease. And in our experiment, we use the 100 dimension of the embedding.
Okay, thank you.
So I'm wondering if other than first and second order proximity, there are other notions like if strongly connected components or dense. If the graph is like it has some dense subclusters, is there a way to exploit that structure other than just common neighbors?
Yes. Second order proximity has been demonstrated as a very popular method to perform on the link prediction method. And in our experiment, we also demonstrate that second order proximity is very important for capturing the structural information within the network.
Thank you.
Yeah.
Yep. Understand that the motivation is for large-scale network, but on the flip side, is it possible to prove, or have you proven that for a small network, so that the free parameters of the network you're trying to embed and the deep neural network that you're using to embed has the same order of parameters, that you can actually get the exact replication? For example, your embedded representation is exactly homomorphic to the network of small enough size. It's like a toy problem that to prove that if the network is small enough, your representation exactly replicates the network being embedded.
Yes. If the network is small, usually we can use smaller embeddings to get a satisfied performance. And for different data sets of different scale, we use different free parameters to fit it.
I guess what I'm asking is that if the network you're trying to embed is small enough, you should be able to know the global optimal representation, so that you can prove that with the second order and first order proximity constraint, you actually recover the original network, as it were.
Maybe it's best to take this question offline. I'm sorry to running out of time. If anyone has questions, please come here after the end of the session. Let's give a hand to the speaker. Thank you.